Alright, this could be our first law in thermodynamics, and this is really, when you look at the word thermodynamics, it's just talking about heat and the dynamics of it, how it changes, how it does work, and those kind of things. This law deals with really this first topic here, which is conservation of energy. This is kind of something we did before. KE plus PE equals energy total. So all the energy we have in a system is either kinetic energy or potential energy. Now we can have electrical energy and thermal energy and all this kind of things, but really what this says is energy is conserved in a system. So you can't create it, you can't destroy it. It just gets transferred. So if you're heating something, you're taking like heating something on a stove, you're taking the flame, the propane, whatever kind of stove you have, electric stove, whatever, you're taking that heat and you're transferring it to the water in the pot, and some of that gets transferred there, some of it gets transferred to the air and is lost that way actually. But really it's not lost because it's still in the air, it's still in those molecules, it's just lost to usefulness. But energy is conserved in any system. And this includes energy, internal energy, energy inside the molecules themselves, how they turn, as they bounce off the walls, those kind of things. Now energy, it says here, can be lost due to friction and heat. So within a system, the friction that occurs there can cause energy to be lost, and also heat as energy is transferred from one substance to the other. We have an equation for this. It's change of U is equal to Q minus W. And we're going to use this here when I get back. Hopefully I'm going to be back soon. And if we're going to write that out, it's just change of internal energy equals energy transferred as heat minus energy transferred as work. Okay, so this is talking about work being done on something. Like a steam engine moves a piston, you use that transfer of energy to do work. And that's kind of what that's talking about. So we look at heat. It can be, heat can be an increase in temperature and a decrease in temperature. So something can gain heat or it can lose heat depending on the system and what is going on around it. So and you can use that fact. So if something is gaining heat, it's gaining energy, maybe perhaps somehow you can have it do work. And if it's losing energy, maybe it can also do work as well. So, and it can increase in temperature as energy is transferred to that object, causing the molecules to move faster. And but also work can be done by the system, or work done on the system. So work is force times distance. Okay. So if we apply a force to something, which you can by heat, you heat a substance, and if you remember from the sim we did, it causes the particles to push something, and it can push a piston to move, and then it moves a certain distance, and you could do work on it. Okay, but it can be both ways. So so a system can do work where it actually causes something else to move, or work can be done on a system where it causes the system itself to be moved and made smaller, perhaps a piston to be pushed in. Okay, and as this occurs, there can be an increase or a decrease in the quantity of U, or internal energy. So if work is done on the system, there's usually a change in energy, and if work is done by the system, there's going to be a change in energy. So if we look at these last terms, and I'm going to want you to look these up in your book, because this is talking about three thermodynamic processes: isovolumetric, isothermal, and adiabatic. And what I'd like you to do is in your book to look these up and define them and give an example of where they occur. And you should easily be able to find this. This is in the chapter on thermodynamics. So if you skip through the chapter on heat, the next chapter over should be thermodynamics, and the first chapter should be Newton's, not Newton's, should be the first law of thermodynamics, and you should find the definitions of these. And just when you do that, go ahead and fill these in. But really, when people talk about this law, really the way they define it is conservation of energy. So in any system, energy is not lost, it's just transferred from one to the other. So if we go back to this thing here, so we can transfer heat and from one object to another, and when we do that we can do work, or we can have work done on the system, and that explains that conservation. So it looks like work's being lost and it's doing work, but really that energy is just being transferred to do something else. And really good example is that the Industrial Revolution, steam engines, and all the things they did with steam engines is just amazing. So that's your notes on thermodynamics, kind of short. I want you to take some time to go ahead and define those three terms, and that should be it. Hopefully I'll see you tomorrow.